We're gonna talk about variation of parameters in this video. The method of variation of parameters is applicable to all types of non-homogeneous linear differential equations. It is more powerful than the method of undetermined coefficients. If you recall, the MUC is only limited to R of x that contains only polynomials, exponentials, sine and cosine functions. To solve a second order differential equation, suppose we have the complementary solution y sub c c1 y1 plus c2 y2. The particular solution is based on the complementary the functions, the two linearly independent solutions in your complementary function. So y sub p will be written as a of x, and then times y1 from your y sub c, and then another function b of x multiplied by y sub 2 from your y sub c. So we find the functions a and b by solving the following linear equations simultaneously. So, but what we can solve in the linear equations are the first derivative of a and b. And then to get a and b, once you obtain a prime and b prime from the equation, we integrate a prime to get a, integrate b prime to get b. So as you can see, here you have the first derivative of a, the first derivative of b, so this will be our two unknown quantities. And then for the coefficient, we have y1, the first derivative of y1 for the second equation. And then y2 for first equation. The second equation is the first derivative of y2. 0, in the right hand side, you have 0 in the first equation. And then in the second equation, you write down whatever you have for r of x here. Note that if the coefficient of y double prime is not equal to 1, then you have to multiply the whole equation by the coefficient of y double prime. So same is true when you have third order. Okay, so you have a third order differential equation. Okay, so the complementary solution will contain three linearly independent functions. So we will use y1, y2, y3 for our particular solution, but we have to multiply by unknown function a of x, b of x, and c of x. So for our auxiliary equations, we have three linear equations. Okay, so our unknowns will be a prime, b prime, c prime. And then y1 for the first equation, first derivative for the second equation, second derivative for the third equation. Okay, so same is true with y2, y3. And then for the first two equations, the right hand side are both equal to 0. But in the third equation, we write down whatever we have in our r of x. Okay, so let's solve this problem. Okay, so you're given a second order differential equation. The right hand side is e to the x over x. So take note that this cannot be solved by MUC or inverse operator. Okay, so for the auxiliary equation here, we have m squared minus 2m and then plus 1 equals 0. So this is identical roots 1, and then for the complementary solution you have c1 e to the x. Now since 1 here is the second root, so you have to multiply by x, and then so we'll take this as our y1. This will be your y2. We're gonna use the two functions here for our y sub p. So a and b are two unknown functions. This is your y1 and then your y2. So for the auxiliary equation, okay, the unknowns will be a prime and b prime. So e to the x, the first derivative is still e to the x. This is by product rule. Okay, so the derivative is x e to the x plus e to the x, derivative of x is 1. Okay, and then this is your r of x. Now as you can see, we can multiply this by negative 1. Okay, and then add to equation 2. Okay, so what do we get? So this will cancel out. Okay, this will cancel out. And then we have now negative b, negative times b here, so negative b prime x e to the x, and then plus the second equation here equals the right hand side 0 plus this will still be e to the x over x. And then we can now solve for b prime here. Okay, you can factor out b prime here. That gives you x e to the x plus x e to the x plus e to the x. So this will cancel out. And then in the right hand side you have b prime e to the x, and then in the right hand side you have e to the x over x. So this will just cancel out, giving you only b prime. Okay, and then we integrate to get ln of x. The next step is to substitute this in equation 1. Okay, your b prime here, not ln of x, b prime here, and you'll be able to solve for a prime. Let's continue. Okay, so this is your b prime. Okay, and then we simplify. So x here will cancel out, and then once you transpose here, you get a prime e to the x equals negative e to the x. So this will just cancel out, so giving you only negative 1, and then integrate. And then this is your y sub p. We now substitute. Okay, so your a is negative x, or rather this is your a, and then your b is ln of x. Now note that these two are similar terms. The coefficient here is negative 1, so you can combine negative 1 and c2 because c2 is an arbitrary constant, so you may use another arbitrary constant here. So you can simplify this as one term, combining the constant, no? So you now have only c1 e to the x, c3 x e to the x, plus x e to the x ln of x. Let's solve a third order differential equation. So let's see what will happen here. So okay, your auxiliary equation is m cubed plus m. Okay, so factor out m here. This gives you m times m squared plus 1. M, the root is 0. This is m squared equals negative 1, so getting the square root, you get plus or minus I. And then the corresponding complementary solution will be C1 for 0, and then plus or minus I corresponds to cosine and sine x. So you have 3. Your y1 here is 1, y2 is cosine, okay, and then y3 is sine. So we'll be using 1 here times the unknown function a, and then cosine times b, and then sine times c. Okay, so this will be our auxiliary equation. So this time you have 3 unknowns, a prime, b prime, okay, and c prime. For the first equation, we have the coefficient 1, okay, your y1, your y2, y3. Get the first derivative, so you get 0. Second derivative will be 0. Cosine, the first derivative is negative sine x, so differentiate again, you get negative cosine x. Sine x, derivative is cosine x, derivative of cosine x is negative sine. So first two equations, both 0, and then we put, okay, in the third equation, your r of x, which is secant x. Okay. Since this is now 0, okay, we now have two equations here, two unknowns. You can solve this by determinant if you want. Okay, let's say we solve for b prime. Okay, for the coefficient matrix, okay, we have negative sine x here, cosine x, negative cosine x, negative sine x. Okay, and for the numerator, we replace the first coefficient by 0. If we're solving for b prime, no? So we replace negative sine x by 0 and secant x. This is by Kramer's rule. And then we retain cosine x and negative sine x. So, okay, positive, negative. We have sine squared here, sine squared x, negative, so positive, so plus cosine squared x. But this is equal to 1. Okay, in the numerator, we have negative sine, this is 0. Okay, that will be 0. Minus cosine x. Secant x is 1 over, okay, cosine times secant x, so this is 1 over cosine x, so this will cancel out. So giving you only your b prime is, okay, your b prime, so what I did here is by substitution. So I get here b prime, which is negative 1, okay? So I get here, using my previous solution, okay, I get b prime equals negative 1, whose integral is negative x. And then for c prime, you can substitute, okay, here, negative 1, and then we solve for c prime. Your c prime here will be negative sine x over cosine x. and then integrating will give you ln of cosine x. So your u here is cosine x. So the derivative is negative sine x dx. So this will now be integral of du over u. So ln of u, where u is cosine x. Okay? And then since we have b prime and c prime from equations e2 and e3, we now substitute in the first equation. Okay? And that gives you a prime equals secant x, whose integral is ln of secant x plus tangent x. So combining your y sub p, okay, and then your y sub c, and then your y sub p. Okay, so this is your a, constant a, negative x is your b, function a, function b, and then this is your function